We've been talking about derivatives, so now it's time to explore the reverse of a derivative. And the reverse of a derivative is sometimes called an antiderivative, or it can be called an integral. So when we said that derivatives tell us the rate of change, and we can use derivatives to look at the motion of an object or different rates and tangent lines and things like that, we have to be able to get back once we've taken a derivative to the original function. And the way we do that is with what we call an integral. And the integral of a function tells us the area under the curve. So if we're looking at an integral, we're looking at the area under the curve. So here you can see a curve. And then if we look at the area from the curve to the x-axis, that would be the value of the integral. Now, when we try to look at the value of the integral, we're going to look at how to calculate it directly. But for a moment, we're going to use rectangles, because if we could theoretically draw enough little rectangles, we could use those to approximate the area under the curve. Remember when we first started talking about derivatives, we talked about the limit, we talked about our two secant points getting closer and closer and closer together as they went along the curve and they made a tangent line. And we talked about the limit as you bring the distance between those points to 0 and how we could use that to figure out the derivative. It's the same idea here. So theoretically speaking, if I were to draw one rectangle under my curve, I could get an approximation for the area, but it wouldn't be that close. If I draw two rectangles, I can get a little bit better approximation. If I draw three, I can get even better. If I draw 5,000, it's getting pretty good. So the idea of using the rectangles is something that's called Riemann's sums. And you are summating the area of each little rectangle as you draw these rectangles under the curve, with the idea of the more and more rectangles you draw, the closer and closer you're going to get to the actual value of the area. So when we look at the pictures that we have here, the first picture shows the area under the curve with the curve drawn and the area colored in. The second picture shows what we are going to call using left endpoints, meaning you're drawing all of these little rectangles and you're drawing them until the left side of the rectangle meets the graph. And then if you look at the last one here, you're using right endpoints, meaning you're drawing until the right side of the rectangle meets the graph. You could also draw the rectangles to where the center was meeting the graph, and that's just another way of notating the same thing. So what we're going to call our left endpoints, this is when we are using the left values to draw the rectangles. And similarly, if we're using the right endpoint, then that means that we're using the right interval values to draw the rectangle. And the interval is determined by how many rectangles you want to divide it into. So if you wanted to divide it into 2 rectangles, you'd have 2 intervals. If you wanted to divide it into 10, you'd have 10 intervals. So let's give this a try. Number 1. The speed of a runner increased steadily during the first 3 seconds of a race. Her speed at half-second intervals is given in the table. Estimate the distance that she traveled during these 3 seconds by using the velocity at the end of each half-second time interval as the velocity during that interval. So remember, if we're trying to figure out a distance, well, distance is rate times time. So if distance is rate times time, then distance would be the velocity times the time of that velocity. So this is telling us to use the end of each half-second time interval. So what that means is from 0 time to 0.5 time. So in the first half second, she was traveling at a rate of 6.2. So from 0 to 0.5, that first half second, she was traveling at a rate of 6.2. So we know that distance is rate times time. So we can say the distance is the rate. So that's her 6.2 times the time. And that was that first half second. plus distance is rate times time for the next half second. So for the next half second, we start at half of a second and we go to a whole second, and we're using the ending. So that'll look like our 10.8. Now be careful. Yes, 1 second of time has passed, but from our last time mark to now, it's still only a half a second. Now we're picking up at our 1 second time mark, and we're going to go from 1 second to 1.5 seconds, and we'll use that ending time. So that's going to look like, again, now we have our 14.9, but only a half a second has passed. And then do the same thing again. So pick up at our 1.5, go to 2, use the ending time. I'm running out of space, so I'm just going to carry it down here underneath. So that would look like our 18.1. And again, it's been a half second of time that has passed. And then we do it again. From our 2 seconds to 2.5 seconds, use our ending. So that will give us the 19.4 times 0.5. And then last, we need to finish out our time. So 2.5 to 3 and use our ending. So 20.2 times, again, a half second has passed. So this we can type into our calculator. You can type it in just as you see it, and if you simplify it all down, it works out to be 44.8 feet. So although she sped up or slowed down, looks like she sped up most of the time, but although she sped up or slowed down as she was running, overall, we can use the distance and the rate and the time to figure out that it looks like she went about 44.8 feet. Let's try another one. By reading values from the graph of f, use 4 rectangles with heights corresponding to the right endpoint of each subinterval to estimate the area under the graph from x equals 0 to x equals 8. Sketch the rectangles that you use. Is your estimate higher or lower than the actual area? We'll figure out B and C here in a moment. So we're going to use this graph for A. We'll use this one for B. We'll use this one for C. Notice they're all the same graph. We're just using the different ones for the different parts. So this is telling us to do 4 rectangles, and we're looking at between 0 and 8. So that means that I need to split the spacing from 0 to 8 into 4 pieces. So I think I'll do 1, 2, 3, 4, 5, 6, 7, 8. So now we need to draw our rectangles. It's saying to use the right endpoint. So that means we start on the right side of the interval. So the last interval here is from 6 to 8. So the 8 is the right side of that interval. So I'm going to draw my rectangle, and it's going to correspond to a height at the right side of our interval. So then we do the next one. So now we're trying to draw from the endpoint of 4 to 6 is 6. So right here is where it meets the graph. Let me draw that over. Draw that down. And same thing, right here between 2 and 4, 4 is our end. So right here is where it meets the graph. Draw it over and down. See how the right corner of each rectangle is what's touching the graph? And then here, over and down. So I was able to split this into 4 rectangles. Now, if you notice, there's all this extra area above right here that's going to be included in my rectangles. So this means that this is going to be an overestimate. And it's an overestimate because it is over the actual area. It's going to be higher than the actual area. Let's see if we can figure out what it's going to look like. So in order to figure out this area, we need to figure out the area of each rectangle. Well, this rectangle, this first rectangle, has a base of 2 and a height of, it looks like 3.75. We're just going to do the best that we can. So we're figuring out the area of this rectangle, and it looks like it has a base of 2 times a height of 3.75. Plus, now we need the area of the next rectangle. So the area of this rectangle, again, has a base of 2, and this time we have a height of 5. So we can figure out the area of that rectangle by taking our base of 2 and our height of 5. I'm running out of space, so I'm going to wrap it around again. But here we have a base of 2, and this time it looks like it's a height of 5.75. And then for our last interval, we have a base of 2 and a height this time of 6. There we go. So now we've been able to figure out the area of each rectangle using base times height. And if we add all of those together, it looks like it works out to be 41. So this was an overestimate. It's a little bit too high because we have all of the extra area over the top. So this is an overestimate. And it looks like our overestimate is 41. Let's try part B. Part B says repeat part A using left endpoints. So now when we look at our interval, so from 0 to 2, 2 to 4, 4 to 6, 6 to 8, now we're going to use the left side of the interval. So the left side of my interval from 0 to 2 is 0. So if I draw it up to where I hit the graph, it looks like right here, and make our rectangle. My left side of the interval from 2 to 4 is 2. So I'll draw it up to where we hit the graph right here, and down. The left side of my interval from 4 to 6 is 4. So I'll draw it right here and down. And then right here and down. Do you see how each of the left corners of our rectangle is touching our graph? So now we're going to do the same thing. Notice this time we have a lot of under empty space. See all this? So this is going to be called an underestimate. Because it is going to be too low. There's a lot of area that's not considered. Let's figure out our areas. So the area of our first rectangle here, well, this one's a square. It looks like it's base of 2, height of 2. And then the next one, our area is going to go from 2 to 4, so it's a base of 2. And now we have a height of 3.75. So 2 times 3.75. For our third rectangle, we have a base of 2, and this time we have a height of 5. And for our last rectangle, we again have a base of 2, and this time it looks like 5.75 for our height. So if we type that all into our calculator, we're going to get 33. So we've sort of put boundaries on our estimates here. We have an overestimate of 41, we have an underestimate of 33, so we know our actual area will be somewhere in the middle. So let's try the next one. Part C, it says find a new estimate using right endpoints with 8 rectangles. So now I need to split my interval into 8 pieces. So now when I do my area, instead of having 2 times for the base, it's just going to be 1. It's asking me for right endpoints. Let me get all these lines drawn in here. Right, it's asking for right endpoint, so I'm going to start on the right. So this first interval, it looks like it's going to be here. Second interval. Third interval. See how the right side of each rectangle is what's touching the graph? Here we go. And again, this one looks like an overestimate. So if we go to calculate our area is going to be base. Well, this time our base is 1 times our height. This first one looks like a height of 3. Plus our base of 1 times our height. The second one looks like 3.75. Plus base times height. I'm going to go with 4.4 for this one. Doesn't look like it's quite halfway. Plus base times height. Looks like 5 for this one. And then we have base again times height. I'm going to go with 5.4. We're estimating it as best as we can, plus base times height. We have another one, base times height. It looks like it's almost 6, but not quite. So I'm going to do 5.9. And then last one, base times height. This one's 6. So we have 8 rectangles. So we should have 8 pieces of our calculation right here. And when we add this all together, multiply it and add it all together, it looks like 39.2. This one would again be an overestimate because it is over, each one of our rectangles is over the curve.